solve some problems on distribution. Before we solve the problem, let us recall whatever we have studied under gamma function. Gamma function is defined as gamma of t is equal to 2 times the integral of 0 to a e to the power minus x square x to the power 2t minus 1 dx. From using this equation, we can compute integral of 0 to 8 x to the e to the power minus x square x to the power n dx. Here we have substituted wherever t is there, 2t minus 1 is equal to n. So t is equal to n plus 1 by 2. So therefore we have here gamma of t, that is gamma of n plus 1 by 2 is equal to 2 to the power n plus 1 divided by 2 divided by 2. Now let us compute certain gamma functions. Gamma of half is always given by root 5. Gamma of n plus 1 is equal to n into gamma of n. That means gamma of 3 by 2 and gamma of 3 by 2 can be written as here it is gamma of 1 plus 1 by 2. So therefore it is half into gamma of half, that gives you half into root 5. Similarly, gamma of 5 by 2 can be written as gamma of 2 plus half. So that gives you it is half, it is n into gamma of n. Here it is 2 into it is 1 plus 3 by 2. So it is 3 by 2 into gamma of 3 by 2. So therefore you get this as 3 by 2 gamma of 1 plus half. So that means 3 by 2 multiplied by 1 by 2 gamma of half, that is root 5. So you get this as 3 by 2 into half into root 5. Similarly, you can compute gamma of 7 by 2 as 5 by 2 multiplied by 3 by 2 multiplied by 1 by 2 into root 5. So in overall we can define integral of e to the power minus z square by 2 z to the power n dz is always equal to 0 if n is odd, and if n is even, then it is 2 times, because I have defined it for minus infinity to infinity, it is 2 times 0 to infinity e to the power minus z square by 2 z to the power n dz, and this can be used by the definition of gamma function, which is 2 times 2 to the power n plus 1. So this can be written as further 2 to the power n plus 1 by 2 gamma of n plus 1 by 2. So from the definition we know that for even integer of n, integral of e to the power minus z square by 2 z to the power n dz between the limits minus infinity to infinity, it is 2 times 0 to integral of 0 to a e to the power minus z square by 2 z to the power n dz, that gives you 2 to the power n plus 1 by 2 for gamma n plus 1 by 2. Now you can see for different values of n, let us try to calculate, and n value needs to be even. It is valid only for even n. If this is odd, then this turns out to be 0. So when n equal to 2, we replace here n with 2, we get this as 2 to the power n is 2. So 2 to the power 2 plus 1 by 2 gamma of 2 plus 1 by 2. So that is 2 to the power 3 by 2. Gamma of 3 by 2 is half gamma half. Gamma half is given by root 5. So when we simplify this, we get this as root 2 5. And when n value is equal to 4, we get this as 2 to the power 4 plus 1 by 2 gamma of 4 plus 1 by 2, that is 2 to the power 5 by 2 gamma of 5 by 2, that gives you here gamma of 3 by 2 into gamma of 3 by 2, that is once again you get this as half into gamma of half. So when you simplify it further, we get this as 3 into root 2 5. And when n value is equal to 6, we have to substitute here 6. So 2 to the power 6 plus 1 by 2 gamma of 7 by 2. And when we simplify gamma of 7 by 2, it is 5.2 multiplied by 3.2 multiplied by half into root 5. That gives you 15 into root 2 5. With this background of gamma function, let us try to solve the problem. First problem, we need to verify the coefficient of Q, E, Z cube is equal to 0, and the coefficient of kurtosis, that is E, Z to the power 4 is equal to 3, when Z is a normalized Gaussian random variable. In the gamma function, we have defined if n is odd, this turns out to be 0. If n is even, then this turns out to be 2 integral of 0 to a e to the power z squared by 2 z to the power n dz, which is in turn given as this is equal to 2 to the power n plus 1 by 2 gamma of n plus 1 by 2. So now n here they have given n value is equal to 3. When n value is 3 is the odd, so this turns out to be e to the power z cube, which can be written as 1 divided by root 2 pi integral of minus infinity to infinity z cube e to the power minus z squared by 2 dz. Here n value is odd, so therefore this turns out to be 0. When n value is equal to even, that is z to the power 4, in this case we can write this as 1 divided by root 2 pi 2 to the power 4 plus 1 by 2 gamma of 4 plus 1 by 2, that is 2 to the power 5 by 2 gamma of 5 by 2. When we simplify this further, we know that gamma of 5 by 2 is given as 3 by 2 into gamma of 3 by 2, that is half into gamma of half, that is gamma of half is root 5. So therefore you get the answer as 3. Second problem, we need to derive the characteristic function for exponential distribution. For exponential distribution, PDF is defined as lambda into e to the power minus lambda x value greater than or equal to 0, and it is 0 for x less than 0. And this is defined only for values lambda greater than 0 or positive values. The characteristic function is always defined as integral of e to the power j omega x into PDF dx, and in this case PDF is defined as lambda e to the power minus lambda x, and it is valid for all values of x varying from 0 to infinity. Here lambda is constant, that is taken out, so integral of e to the power minus j omega minus lambda x dx. When we integrate this, we get the answer as lambda divided by lambda minus j omega in the denominator. Let us try to solve the third problem, wherein we need to find the characteristic function for Laplace distribution. Laplace distribution PDF is defined as g e to the power minus g modulus of x divided by 2. This can be split into two functions as b by 2 e to the power bx u of minus x plus b by 2 e to the power minus bx u of x. Characteristic function is always obtained by integrating PDF and into e to the power j omega x dx. Between the limits minus infinity to infinity, and this will give us for all this function exists for all values of x which is minus infinity and 0. This exists for all values of x between 0 to infinity. So we can split this into two functions. as integral of minus infinity to 0 b by 2 e to the power e plus j omega x dx plus integral of between the limit 0 to infinity b by 2 e to the power minus b minus j omega x dx. And when we integrate and substitute the values, we get the final answer as b square divided by b square plus omega square. Let us take the fourth problem. We need to derive the characteristic function for uniform distribution. For uniform distribution, fx of x is given by, that is pdf is given by 1 divided by b minus a for all values of x between a and b, and b value should be always greater than a. And the characteristic function phi x of j omega is defined as integral of pdf e to the power j omega x dA. When we integrate it and substitute the values a and b, we get this as e to the power j omega b minus e to the power j omega a divided by j omega into b minus a. Problem number 4. Derive the characteristic function for Poisson distribution. Poisson distribution PDF is given by summation k value varying from 0 to infinity pk delta of x minus k, where pk is equal to b to the power k divided by k factorial e to the power minus b. Characteristic function can be obtained by integrating the product of PDF with e to the power j omega x dx. And here we have replaced PDF with the PDF function for the Poisson distribution, and we'll interchange the summation and the integral signs, and when we interchange and rewrite it, we get summation first, k value varying from 0 to infinity, k is taken out, integral of minus infinity to infinity delta of x minus k to the power j omega x. We'll apply the property of impulse functions. When we apply the property of the impulse function, we know that x value is equal to k. It has to be replaced with in the place of x. So therefore, we get summation k value varying from 0 to infinity pk e to the power j omega k. And let us substitute the value of pk, that is given by e to the power k divided by k factorial e to the power minus b e to the power j omega k. Here e to the power minus b is a constant term that can be taken out, and we can write this as k value varying from 0 to infinity ek divided by k factorial e to the power j omega k. And let us expand this. When we expand e to the power j omega k and the form of a series, we can write this as because this b can be taken inside, so we can write this as b e to the power j omega k. Let us expand this in the form of series. We get 1 plus b e to the power j omega plus b square e to the power 2j omega 2 factorial plus b cube e to the power 3j omega b factorial, so on. This e to the power minus b will remain the same, and this can be written in the form of a series, that is e to the power b e to the power a to the power b e to the power j omega. So e to the power b e to the power j omega minus b. So b is common factor, that is taken out. E to the power b e to the power j omega minus 1 is the characteristic function. Thank you. In the next video, let us study the functions of single random variable.